Welcome you all in this new video, and in this video we are going to discuss regarding the what was the question paper in this year. Okay, physics optional, and it is the paper 1. So we will discuss all the question paper section by section in the videos. Okay, so in this video we will discuss only the 5 questions of question number 1. Okay, this is the question number 1 and it has 5 sections or 5 questions within it, and we will discuss all these. And this was the paper in this year, and I think it was not that much tough. It was at the level of 11th 12th, you can consider it. Okay, so what was the actually questions and how we can solve it? Okay, and what were the formulas that was regarded it? Okay, and we can use that formula to solve these questions, and these are very easy questions, guys. In this year the physics optional was very easy. Okay, so we will discuss one by one. Let's discuss first what is the first question, means what does it tell. Okay, it says that a force okay, there is a force and this is the force given to you. So let me write it here. Okay, so what is the question number 1? Okay, it says that there is a force given to you, and what is that force? Wait a minute, sorry for this interruption. Okay, there is x square y x. Okay, so this is the force. Let me solve this question here. Okay, it is not that much complicated, or we can say here you have to use simple concept. Okay, first you have to understand what is the force of conservative. What is the force is conservative? What does this mean? Force is conservative when, and what is the conservative force? Conservative force is the force, okay, when it do some work, that work is not depend upon the path. Okay, path it is going to follow, like this. Here is the two particle, okay, and it is does not depend upon the path. Okay, it means that it is independent of the path, okay, followed by the particle or while doing the work. Okay, here is the two particle, and what is the distance or what is the path? Okay, that conservative force is independent, so we call that kind of force conservative force. And how we can prove that mathematically? You simply have to use a formula here. Okay, that is curl of the force, okay, is always equal to 0 for what? Conservative force. Now what you will do, you have to prove that, determine whether this force is conservative or not. Okay, so what you will do, you will put the values of force here, and so it will come like this, j cap k cap. Okay, and here is the value of what? Okay, like this, and here you will write the value of force that is given, okay, around a particular axis, like x axis. There is written to you that x square y, okay, and z y square, z y square, and x z square. Okay, so this is given to you. When you will solve this, okay, you will come out, I had solved it, so it will not come equal to 0. Okay, so it means that it is not equal to 0. So how we can say that this is not conservative force? Okay, you can solve it, it is very easy to solve. Okay, and here from I cap, j cap, k cap, these are just a unit vector. Okay, and here these are considered with x cap, y cap, j cap, so don't be confused with. Okay, we usually have seen that, okay, with x direction we use I cap, but here is used the x cap, means it is also similar or same, just there is difference in the representation. Okay, so don't be confused. So this is first question, that is conservative force, is it or not? So how you can solve it? You have to easily what define the conservative force, means that is not dependable on the path, okay, followed during the work done. Okay, so this is the conservative force, and how you can prove it mathematically? This is the conservative force, okay, means curl of that force is equal to 0. So this is first section of the part 1. Okay, so second one is what? Calculate the gravitational self energy of the earth given this. Okay, so let me solve here, and it is a this is a part B. So this is called gravitational self energy, and what is the mass is given to you, and radius is given to you. Okay, these are already given to you. I'm just giving you the formula and way to solve it, and calculation you have to do by your own self. Okay, so what is the gravitational self energy? Gravitational self energy is nothing. Let's say there is a system, here is the particle. Okay, here are the particle, these are present at the infinite distance, or we can say these are spread in a particular region or beyond the region, okay, limit. So the energy required to gather or assemble all these particles into a particular configured structure, okay, like this. I gathered all these particles into one small or one particular shaped structure or system, okay, like this. The energy or the potential energy or the work done which is required or which was done during the assembling of all these particles into the one body, that is called self energy, okay. Gravitational self energy means the energy required to assemble all the segregated, or we can say all the spread particle from the infinite distance, okay, to gather them and assemble them in a particular body, okay. So that, or to we can say by assembling all the particle in a particular body, okay, the energy or the work done in that process, that is called what? Gravitational self energy. And how you can derive the, I'm not going to derive completely, but I will give you the slight idea how you can do this. Let's say here is your sphere, okay. So I don't know how much energy is required and how much work was done to gather, to assemble the particles, okay, with which it was formed. So I can easily assume that, okay, here is the center and here is a small solid sphere inside it. Let's say its radius is r, okay. So let's say that this small sphere of radius r gather a small, we can say small this kind of layer around it, okay. And what we consider it, this layer we can consider it of width dr, and we call it what? Spherical shell. Spherical shell, okay. Spherical shell, okay. Spherical shell, and this is the solid sphere inside it, okay, and this is the spherical shell. So how we can, it is the potential energy, guys, don't be confused, okay. So what will be the potential energy, okay, required or change in the potential energy of this sphere of radius r when it is gathering a layer of the width of the dr? We can say that is spherical shell. You have to do nothing, you have to do what is the change in the potential energy. Potential energy is nothing, it is the work done because of the distance change, or we can say height change, okay. So don't be confused here. So what is the change in the potential energy of this small sphere we are talking about, okay. So this will be what? Potential because of this small sphere multiply the mass it has gained, okay. Mass means what? The mass of that spherical shell. And what will be the mass of that spherical shell? We can easily derive it by formula 4 pi r square, because our radius is considering, okay. We don't be confused, radius of the spherical shell and that small sphere of radius r, okay, that is same, okay. And so this is 2 pi r, dr is the small width, and here is the density, rho is the density. Density will remain constant of y, either we are talking about the sphere or shell, okay. So here is the, this is the mass, this is the mass. You know that you can easily calculate what is the potential of this small sphere inside it and what is the mass. It is, we had already calculated, okay. So this was the potential energy, or we can say gravitational self energy for this small sphere, okay. If we have to calculate this sphere for whole sphere, okay, that is of radius r, so what will be it? It will be equal to what? To integrate it from 0 to radius r, okay, within the limit we have to calculate. So this is this, okay. We will integrate it to get the equation for whole gravitational self energy because of this a complete sphere, okay. So it will come equal to what? Minus 3 over 5 g. I am putting it directly so you can calculate it, it is very easy to calculate, r square, okay. So this is the formula of gravitational self energy. You easily, you don't need to derive so much long it, you can easily put this formula there and put the values of gravitational constant, okay, mass value there and r value there, and these are already given to you, okay. Look at here, mass value is already given to you, okay, and radius of the earth is already given to you. Just have to put the formula minus 3 over 5 g m square over r. You just have to put the values of this mass of the earth and radius of the earth in this expression, okay, you will easily get. So this was the second part, and now we talk about what was the third part, and it said that what are the consequences of the Lorentz transformations on the length and time when it is observed from the frame moving at the relativistic velocity, and when observed from a frame moving at a relativistic velocity, okay. It is talking about the Lorentz transformation, okay. Lorentz transformation. So Lorentz transformation give us the 3 or 4 equations, okay, and that 4 equation, we can say that was the modification of the Galilean transformation. Galilean transformation was limited, okay, that don't have so much wide scope to describe the things, but here on the basis of the Lorentz transformation we describe the when two, okay, I'm just giving you the idea, okay, through that idea you can easily derive that this what the Lorentz transformation did. The structure and the experimentation structure was similar, okay, but the conclusion they had concluded, okay, that was different. So what a Lorentz transformation says that there is a let's say S dash frame and S frame, okay, S dash frame is moving with the velocity v, okay, and so he gave the equation. So let's say particle is moving along the x direction, or the frame is also moving along the x direction, okay. So what will be the coordinates of that particular point along the means the coordination relation of the different frame of reference, that will be S and S dash, okay. So it will be x dash x minus vt over 1 minus v square over c square, okay. So this was the x, and we say that y coordinate was constant, z was constant, okay, in both the direction. And this was the new, guys, this was the new, that the time is also varying. So what was the time varying? T minus vx over c square over 1 minus v square over c square, okay. So this was the Galilean transformation. And what was the asked in the question were asked that what is the significance in case of the length and time you are observing from where? From the moving frame of reference. You have to do nothing. This is talking about the significance on the length. So you know about the length, you have to define two phenomena, okay, length contraction, okay, and time dilation. You have to define two phenomena, time dilation and length contraction, okay. So what is the meaning of length contraction? Length contraction says when your speed of any object or any rod, okay, any length particle is moving with the comparable speed of the light, what happened, its length seems to be decreased when you are observing from a stationary frame of reference. So what does this mean? So there are two frame of reference, okay, and here we consider, here is a, let's say, a particular rod of length, okay, this is the S dash frame and this is S, and S dash frame is moving with the speed of v, okay. So let's say here the coordinated from the O dash on O, okay, from the coordinate from this S dash frame, these are, let's say this is x1 dash and this is x2 dash, okay, and if we talk about from this side, so this is x1 and this is x2, okay. So this, what is the actual length? Actual length will be what? A difference between the coordinates in the S dash frame, means L0 x2 dash minus x1 dash. So this is the actual length, guys. So what is it asking? It is asking that what is this length? So we have to do nothing, we know the formula, okay, we have to put the formula through the Lorentz transformation like this. If this is x2, put there x2, you will easily get the equation, okay. So this is the length contraction. Length contraction means what? This will be like this, okay, 1 minus v square over c square, sorry, this will not, and this will come in the multiplication, okay, 1 minus v square over c square. So you can easily get this, this is not that much tough, okay, by applying the Lorentz transformation in this kind of the expression you will easily get. And what about the time dilation? You have to do the similar thing there also. You have to take two instant of time, okay, let's say t2 dash minus t1 dash, okay, this will be the expression, and by putting this expression of Lorentz transformation here you will easily get, okay. And after that you can say that, okay, when your light is moving, object is moving with the comparable speed of the light, what will be happen there? These are the special cases, you can easily do it, okay. So now move toward, so what is the next question? We have done this, okay, this is the Huygens principle for a plane wave traveling from the rare to denser medium. Show that, okay, this is the, and I and R the angle of the incident and angle of refraction, okay, I1 this is mu1, this is the I think refractive index, okay. So this is the question, and what it is asking, it is showing us that prove this phenomena through what? Through Huygens principle, okay. So you can easily draw the diagram here, Okay, so you can do like this. So here is the incident waves that are coming toward it. Okay, and what say, it said that it is a rarer medium. Let's say it is moving here, the speed of the light is v1. Okay, and when it is moving toward the denser medium, that is medium second, okay, what its speed is going to change. Okay, like this. Okay, and we know that when a particle moving from rare to denser medium, what happened, it's get deviated toward the normal. Okay, it's get deviated toward the normal like this. Okay, so here is the angle, what, I angle of incidence, and here is the angle of refraction. So we can let's say it is O dash, and let's say take a perpendicular from this side. This is a perpendicular, let's say this is P. So if I ask you what is the distance between P and D, sorry, this is O dash. Okay, what is the distance between P and O dash? You can say that distance is what, velocity distance over time. So distance is what, velocity into time. So we can say it take time t1 while traveling from, so no, not t1, we can take common time. Let's say that it take time t while moving from P to O. So what will be the distance? v1 t. Okay, so it will be the distance. And if we do the same thing here, okay, and okay, we are doing the same thing here. So let's say this is what, this is, and this is, okay, we are, it is moving in the denser medium, so its velocity will change. Okay, and when its velocity will change, okay, so here is your angle of refraction, so don't be confused. And when your velocity will change, so what, we will do the same thing, v2 t, because we had said you that v2 is the velocity of that particle, when particle or that ray, okay, that we can say light, when it is traveling from rare to denser medium. Okay, so it v2 and there is v1 t. Okay, so easily, and here is the, sorry, angle of incidence, and here is the angle of refraction. Okay, so by from the, let's say this is point is S. Okay, and from the triangle OP O dash, sorry, this pen is not working. Okay, OP O dash. Okay, from here we can easily get the value of sine I. Okay, this is the angle sine I. So what it will be equal to, what, it will be equal to v1 t over O dash. And similarly from triangle OS O dash, so sine R, it will be equal to v2 t over O and O dash. Okay, so what we have to and we were asked that we have to prove that sine I over sine R is equal to what, the refractive index ratio. Okay, sorry, refractive index ratio. Okay, okay, so what we will do, we will take the ratio of these two terms, sine R, and that will be equal to what, v1 over v2, when you will divide or take the ratio of these items. And now we have to, what is the refractive index? Refractive index is nothing, it is the ratio of the speed of the light, okay, in the vacuum, and what the speed of that similar light, okay, in the medium. Means in medium, what was the light speed in the vacuum is c, and light speed in that rare medium, that is v. Okay, rare or denser, whichever medium you are talking about, means the light speed in vacuum and upon the light speed in medium. So that is, if we do and divide both side by this, okay, and by the v, and put this formula here, so you will get refractive index of the medium second over refractive index of the medium 1. So this is the expression that we were asked. Okay, it is very simple. Okay, it's I think around the 11th standard. Okay, and what was the last is about 3 and 4th level pumping. It is nothing, guys. Okay, it is same as the excitation energy or excitation level. Okay, you will consider here the ground level and excited level. Okay, so and you will in the 3 level pumping. 3 level pumping means there is the final excited state is 3rd level. Okay, and there is in the middle that we can call that stable state. Okay, and it will get stable. Okay, and there is also, it will stimulate emission will be there. Okay, it will produce the laser light, and there is also the non-nuclear or non-radioactive transition. Okay, so it is very simple. So you have to draw the, also in this diagram you have to draw the stimulating emission kya hota hai. Okay, so you have to put the phenomena there. You have to show, you have to prove that okay, when there is the fourth level pumping, at that point we get the low level, okay, laser state. Okay, we can say that stimulation of stimulated emission is at the lower energy level. Okay, so you can show this. So this was all about the first question. In the next video we will discuss the another question. Okay, we will start from here, derive the expression from the gravitational potential at any point. Okay, so I hope you like this video. If you like our video, then give a thumbs up and do subscribe our channel.